Impactor.
Hi, good morning, everyone. Today I'll be presenting Lawrence Livermore National Laboratory's results for a case study we participated in, along with NASA Goddard and LANL, investigating deflection of a small body object. So with the DART mission only a couple years away, we want to be certain and confident that we know exactly what is going to happen when that kinetic impactor hits the secondary of the DDMOS system, especially since the Planetary Defense team at Lawrence Livermore is contributing to the numerical modeling of this event. So we have been preparing not just for the DART mission specifically, but for the eventuality that a hazardous object will impact our planet at some point. And in preparation, we have been participating in studies, doing our own research and work, participating in workshops, simulating different scenarios that investigate how, for instance, composition or porosity may affect the total deflection of your hazardous object. So this table up top was actually presented in Megan Brooks-Sayal's presentation earlier this morning, in case you missed it, and just to reiterate a very good study work that we have done before. For the same material, granite, having a slightly different porosity gives you a slightly different beta. And thank you, Angela, for defining what beta was earlier in your talk. And inversely, for the same bulk density, having different composition can again give you slightly different beta. So the overarching theme from our work to date is that knowing as much as possible about an object before deflection is to our benefit. Previous work from the DART IAA International Workshop back in June 2017 uncovered that beta is dependent on impact angle. So really what happens is that your resultant momentum vector is not in line with the direction of approach. In fact, it actually skews to be more in line with the normal of the surface of the object. And that's a very important result. And since 2017, more work has validated this result. Furthermore, most objects are spinning. So if your impactor accidentally or hits a local slope, then you might not get as much push in the direction as you intended. So for this case study that I'm presenting today, we're pushing the envelope further, and we are investigating how the total shape of a small body object, not just local topography, can affect damage your beta, thereby affecting your total deflection. Oops, let's go back. So Megan and Dawn have already showed a similar slide. I'm using Spheral for my simulations. Spheral is an adaptive smooth particle hydrodynamics code, and I am using the tensor generalization of the Benz-Usbach damage model and the pressure-dependent column strength model specific for rocks. Brent Barbie and Josh Lysoft from NASA Goddard were kind enough to send us the shape model for comet Churyumov-Gerasimenko, otherwise known for its shorter name, Comet 67P, which I'm very appreciative of. Otherwise, it's quite a mouthful. And having this shape model allows us to investigate how an irregular shape, and I say irregular because it has these two lobes, one large, one smaller than the other, connected in the middle by this neck. Really anything that's non-spherical is irregular, I suppose. So having this particular shape model allows us to investigate how an irregular shape can affect an intended deflection. We took this shape model and we scaled it down from its original comet size of a whopping 4 kilometers down to around 150 meters in length and around 17 meters, let's say, in diameter. And we were provided with 2 different object files from Josh and Brent. One had around 5,500 facets and the other roughly around 100,000 facets. And what we did is we took the 2 object files, we ran them, and we wanted to compare our initial damage and beta results and see if they were similar enough. And we got lucky that they were. And so we decided to use the object file that had 5,678 facets to run our simulations to reduce computational cost. The initial conditions are informed by what we think we know about comets, that they are highly porous objects. So for our simulations, we used an 80% porosity. We also used granite as our material of choice to be consistent with our previous case studies. I think Kathy went over that earlier, that the preceding case study looked at an object that was representing Didymos B for the DART mission, and they used granite as their material of choice. Our strength values for granite are rather high when you compare them to what you would find for strength in a comet in literature or for a porous rock and material. These strength values for granite are specific to spheral. They're from our code validation work that we've been doing. We used the Tillotson equation of state for simplicity, and we modeled the entire shape in its entirety. Some of our previous work took ice cream scoops, but for these simulations, we did them all in 3D, and we did the entire shape. This required about 24 million ASPH particles, which resulted in around a resolution of 23 centimeters. For our aluminum impactor, we used aluminum, and we used a cube shape, which translated to a resolution of around 13 centimeters, using about 2,000 ASPH particles. We explored two different scenarios for our case study. Scenario A used a light and low speed impactor with a calculated delta V of 0.25 centimeters per second. On the other end, we used a heavy and fast impactor in scenario B for a calculated deflection of 1.65 centimeters per second. For both of these scenarios, we simulated the impactor hitting at two different locations, one being from the top of the target along the y-axis, and the other from the side directly along the x-axis. So for this case study, we had two different scenarios, two different impact locations for these scenarios, and it really allowed us to study the range of what an actual deflection would be. We'd have a very small deflection on one end and a larger deflection on the other end, while also giving us the opportunity to investigate how the irregular shape could affect this deflection. So for our kinetic impactor deflection case study, we had to run a few different iterations. Old simulations used the Benz-Ausbau strain model that is traditionally used in SPH codes, and this follows the deviatoric stress that is dependent on pressure. Mike Owen implemented an enhanced strain model into our ASPH code, which follows the deviatoric stress without the absolute bounding of plasticity. So using this enhanced strain model, we got beta of about 1.5 for scenario B and a beta sitting at 1 for scenario A. So these simulations are still running. Our betas are expected to evolve and grow over time. We will run these until our betas converge over time, which can take up to around 5 seconds. But as is, if we compare the two scenarios, A and B, we find that for B, for the heavier, faster impactor, there's slightly more damage in the object, which we would expect. And we're happy to see that there's not a whole ton of damage. So in turquoise, you're seeing that there is no damage. And this is what we would like to see for a deflection study, since this is not a disruption study. For the kinetic impactor hitting the target on the top along the y-axis, we have a beta of 1.85 for scenario B and a beta sitting at 1 again for scenario A. Again, these betas will evolve over time. These simulations are still running. And like the previous slide, the damage is minimal for both of these scenarios, which is something that we look for in these studies. So deflection can be achieved by using the kinetic impactor technique, but also can be achieved by using a technique through ablation. So this technique would use a nuclear standoff device. So basically, you have a device some distance away from the surface of your hazardous object. This device detonates and creates X-rays. You're in space, and space is a vacuum. These X-rays deposit as a very thin layer on the surface of your object. This creates it to heat up very quickly, ablate, possibly melt material underneath. This material blows off and imparts an equal and opposite push onto the bulk of the object, and that is nuclear deflection in a nutshell. Our initial conditions for scenario C are defined by the deflection criterion for scenario A and B in our deflection study, and from some preliminary simulation results that we had. So scenario C is defined by having a 5 kiloton device, 2 keV black body, 65% re-radiated, with the hopes of having a gentle deflection of 1 centimeter per second. And to achieve this goal, we have to have really high resolution at the surface, around 10 to 50 microns, which to capture and accurately assess the delta V. So for these simulations, we used around 3.775 million ASPH particles in total. The challenge is that the low density, effective radius, and escape velocity makes it really easy to push this object way too hard. And on top of that, we have an extra challenge. The irregular shape, having these two lobes, introduce shadowing effects. These are simulations that were done by Megan Brooks-Sayal, and here she is showing in color the skin of the nodes, and this color represents about a depth of 10 meters. So on the left-hand side, you have a simulation, an image showing the 5 kiloton device around 250 meters from the surface of the object. And on the right-hand side, you have the same device 1 kilometer away. So looking at the device 250 meters from the surface, this simulation produced too much push. It exceeded that 1 centimeter per second intended deflection. So essentially, by increasing your standoff distance, you effectively decrease the push that the object feels. So for a 1 kilometer standoff distance, we still find that the push is too hard. And this is an image from the direction, from the viewpoint of the device traveling toward the object. And at still a kilometer, we're finding that the push exceeds the gentle deflection of a centimeter per second. So we're still working on dialing in this yield and dialing in the standoff device to achieve that gentle deflection. So our takeaways so far are our net betas for our light, slower impactor are sitting at around 1, but these simulations are still running. For our heavier, faster impactor, we have betas that range between 1.5 and 1.85. These simulations are also continuing to run, and they'll run until we see our betas are converging. For our ablation deflections, the complex shape of Comet 67P shows shadowing effects from the X-ray source. The low density of the comet, or of the small body object, I should say, makes it easily pushed from the momentum of the X-ray blow-off. And we are currently refining the ablation deflection to match the gentle deflection of 1 centimeter per second. And as I am wrapping up here, I just want to circle back. I briefly mentioned at the beginning of my talk a little bit about the DART mission, and I would like to end with a similar note and perhaps stating something very obvious, but we don't really know exactly what the secondary of the Didymos system looks like. All we have is this image, a blurry image shown here, and when we get there, we may find that that secondary is not spherical, it's not ellipsoidal. In fact, it might have an irregular shape that looks something like Comet 67P. So that is why we do these studies like the one I just presented here, so that we can be prepared for the DART mission, but also just for the eventuality that one day we will have to deflect a hazardous object. Thank you.
Thanks. Any questions? Dan.
Yeah, thanks. Dan Mazanick, NASA Langley. Just a quick question on your results for the ablation. You're showing like 1 kilometer per second pushes. Are those units correct? For the 1 kilometer standoff, you're showing in red like 1 kilometer.
That's the standoff device. I mean, that's the standoff distance for the device is a kilometer.
Yeah, but you're showing kilometers per second and meters per second.
So I don't think I lost the image, but those are the surface velocities. So it's just the velocities of the particles right at the surface.
Okay,
so that's not the total deflection.
So what type of total deflection were you seeing there?
Well, it exceeded 1 centimeter per second. I think we were, you would have to probably talk to Megan for the exact, but it definitely exceeded gentle deflection. It was still too much push.
Okay, and then also the density that you showed for granite, you showed it like a 0.5 gram per cc. Was that the overall density with the porosity included,
Yes.
I assume?
Yes.
Okay.
Thanks. Yes.
Could you repeat for me what the yield of the device you modeled?
5 kilotons.
5 kg. Any other questions for Tane? All right, thank you very much.
Thank you.
Okay.